Welcome to part 1 in a short series of Python programming lessons for beginners. In this series, I'll take you from knowing very little about programming to being able to explore projects that personally interest you, whether that be in web development, making mobile applications, doing data analysis, exploring artificial intelligence, computer vision, things like that. And arguably, Python is one of the best programming languages for beginners. For one thing, its syntax is easy and straightforward to read. It has a massive online community that will help you out if you get stuck. The language is very versatile and powerful, and you can extend Python with your own custom libraries in C and C++ when you become more experienced. And it's also in very high demand in the job market. So first off, we need to set up Python on our system. And in this video, I'm going to set up on Windows, but if you're using a Mac, the process is very similar. And if you're using Linux, I've got another video up here that will help you get set up on that system. But we also need an integrated development environment, or an IDE, which is simply a piece of software designed to make writing code easier. It does this by color coding our syntax, making our code easier to read. And if we've made any mistakes in our code, it will also highlight our mistakes for us. So the IDE we're going to use for this series is called Thonny, and it really is a great IDE for beginners because it's not bloated with any unnecessary features that we don't need as a beginner. Now, if your machine has never been used for Python programming, it's unlikely you have Python installed on your system. But this really doesn't matter because Thonny has Python built into its installation. So to install Thonny, open up a web browser and type in thonny.org. And I've provided a link in the description. And to install their IDE on Windows, click on the Windows link and select the topmost link where it says recommended for you. If you're on a Mac, go to Mac and click on the package link just under installer with Python. You may also get a prompt asking you whether you want to allow this download. And once you've got that downloaded, open it up, click on install for me only, create desktop icon if you want a desktop icon, then click install, and once it's installed we can open it. Now let's open up Thonny and see what we got. Now the Thonny interface should open up for the first time, but if you get an error saying something like VC runtime was not found, something like that, there's a link in the description that will show you how to fix that error. So here we can see Thonny's split up into two main parts. At the top we've got a script editor, and at the bottom we've got something called the shell, or the interactive shell. And here we can execute single Python commands and get immediate feedback when we press enter. And this is really useful if you want to write short code snippets and test them out. So let's try a few Python commands quickly. In the interactive shell, type in this command, making sure all letters are lowercase, and then press enter. You should see the word hello displayed just below your command. If you get an error message, make sure you've typed in the command exactly how it appears on the screen. A missing quotation or capitalized letter, for example, will cause issues, as you can see in these examples. Okay, so let's try one more before we look at the script editor above. Say we want to capitalize all letters in a string. We can write this command. You can also see that Thonny's shell has code completion and correctly guessed the command that we wanted. If you don't see code completion like this, all you need to do is click on Tools, Options, go to the Editor tab, and make sure these 5 checkboxes are ticked. Okay, now let's try a very simple program in our script editor. The goal of this program is to ask the user for input from the keyboard, and it will count the number of characters that the user has entered. So first of all, we need to create a variable, and I've given mine the name sentence. Next, we're calling a function called input, and the function input simply displays a message to the screen and awaits for input from the keyboard. And after you press the enter key, all the keyboard input is stored into the variable named sentence. And on line 3, we are doing two things. First, we're finding the length of sentence. Then we're displaying it out to screen using the print command. And in order to run this script, all we need to do is press F5 on our keyboard or click this play button above. A computer program is a sequence of precise instructions telling the computer what to do. These programs can be as simple as controlling when a street light should turn on, to something as complex as a self-driving car, which would need to perform millions of complex calculations per second. But despite the huge range of different software in existence, all these programs boil down to 5 basic actions. First, they all receive input. This could be from a sensor, like a camera, or a file on a hard drive, a keyboard input from a user, or maybe even from other computers across a network. Programs often perform mathematical calculations. A self-driving car may need to calculate its stopping distance while driving at 30 miles an hour in heavy rain. Programs will also perform checks to see if certain conditions are true or false. These are often called conditionals or conditional statements, and they allow the program to choose what part of its program to run if a certain condition is true. For example, if a room's ambient temperature drops below 20 degrees Celsius, run the code that is responsible for turning on the boiler. Programs will often loop or cycle through code many times or indefinitely if needed. In the previous example, you would want the program to test the ambient temperature every few seconds to see if the temperature had changed. And finally, programs typically output some results, whether that's to control motors in a robot arm, to emitting an audible beep when an item has been scanned at the checkouts, and so on. And that's pretty much all there is to it. Your job as a programmer is to break down a task into smaller subtasks using a combination of these 5 actions. And it's important to note that these programming concepts that you learn in Python are transferable to other languages such as Java and C++. So you don't need to start from scratch if you want to expand out into other languages. You can think of variables as containers set aside within computer memory that can store values. As a programmer, you can create these variables anytime you want to temporarily store data or the result of your program's calculations. But these values will only be available while the program is running. However, generating variables in Python is very straightforward. All you need to do is write down a descriptive name for an item you want to store and assign it to a value. I've written a few examples in my Thonny editor. So here we have 4 different variables, each having their own unique data type. We have an integer or a whole number, a float, a string, which we can write in double quotes or single quotes, and a boolean, which can have a value of true or false. And the value true or false must always start with a capital letter in Python. If I write true in lowercase, Python won't recognize this and will throw a name error. Now in Python, you don't need to declare variables like you do in other languages. In Java, for example, you would need to specifically state what type of data the variable is going to store, where the data types are declared before the variable names. And in Python, we don't need to do this. Python will automatically infer what the data type is by looking at the value you've assigned the variable. And we can check this out by using the type command. The type command will return the data type of the variable between the brackets. Then we can nest this command within the print statement to display our result within the shell below. When we execute the script, our data types are as we expect them to be. Not only do variables provide a useful way of labeling data with descriptive names, we can also perform various mathematical operations on these variables. Say if we want our program to store the total size of a company's workforce, not only do we want to store the number of employees, we might want to store the number of managers. And we may want to represent the workforce in this way because the number of employees and the number of managers will vary over time and independently of one another. we can get our program to add these two variables together and get the total size of the workforce. But the point to note here is when our number of employees or managers changes, the total size of the workforce will automatically be calculated and stored when we run this program. We can also add together two string variables. Say if we add a first name and a last name variable, we can chain these variables together within a print statement. And to add a space between names, we can add a space surrounded by quotes. This will also work if you want to save this result into another variable, for example full name. Python is a strongly typed language, which means you cannot add together two variables having different data types. For example, it wouldn't make sense to add together the name variable with the number of employees. If we try that, we would get a type error. However, Python is more flexible than other strongly typed languages. For example, we can add a float and an integer together, making our new variable a float. There's some rules for naming variables that you cannot break. First of all, variables can't start with a number. Also, you cannot use any special symbols anywhere within the variable. If you do, you'll get some errors like you see here. And you cannot use any one of Python's keywords. As well as being a strongly typed language, Python is also a dynamically typed language. This means a variable's type does not have to be declared, as we've discussed a few minutes ago, but it also means a variable is allowed to change its type over the course of a program's lifetime. Here, we have a variable called cost of weekly shop. First, I've assigned a float value to this variable and asked the program to print out its value and its type. Then I've decided to use the same variable to store an integer value. And finally, I've asked the program to store a string value in the same variable. When we run this program, you can see Python does not have a problem assigning different data types to the same variable. Finally, you can add multiple variables on a single line when you separate them by commas. I don't usually do this myself, simply because it makes reading off the values a bit harder when you're looking over the code. But some programmers might do this if they want to group similar variables together. In the previous section, we looked at how variables can store values and perform simple arithmetic. But these values were assigned by us, the programmer. While our script was running, we couldn't externally update these variables. Programs become more flexible and therefore more useful if we can update these variables during runtime. And there are many ways to do this. But in this section, we're going to look at getting keyboard input from the user using Python's input command. So let's try an example. On the first line here, we have the input command with some text within its brackets. This is called a prompt, and it gets printed out to the screen when this command is executed. It's also worth noting that all commands in Python are case sensitive. This means that commands must be written exactly how they appear on the screen here, or within other books or documentation you may read. In other words, Python won't allow you to write the command in all capital letters, for example. So our input command is asking the user for their name, and the program will pause until the user hits the enter or return key. Whatever the user has typed between receiving the input prompt and pressing enter will then be stored in our name variable. We can then continue on to the next line and print out the message hello and your name or whatever you typed in to the keyboard. And when we run the program again, we can see this here. You can even add a new line after the input prompt. So when the user types in their response, the text will appear underneath the program's question. In order to add a new line, we need to use a special character, which in this case is a \n. And this special character won't be printed out to the screen. So let's now create a more useful script using the input command, like a Celsius to Fahrenheit converter. We'll only need a couple of variables, the input command, and some simple arithmetic operators. But there are a few issues that we'll run into and need to fix as we create this script. First, we've used the input command to prompt the user for a Celsius value, and we'll store this value into a variable which we'll conveniently name Celsius. Our next step would be to use the mathematical formula for converting a Celsius value into a Fahrenheit value and store the result into a new variable called Fahrenheit. But here's where we run into our first problem. Any user input collected by the input command gets stored as a string data type, and we can determine a variable's data type using the type command. So if we test the data type in our Celsius variable by printing out its type, we can see that no matter what value we type into our prompt, it will always get stored as a string data type. Now, why is this a problem? Well, Python is a strongly typed language, which means it won't allow you to perform mathematical operations on two different data types. To solve this, we need to do something called typecasting, which will allow us to convert one data type to another. And I'm going to show you two ways you can do this. First, because we're using floats within our Fahrenheit calculation, we really need the Celsius variable to be a float data type. We can do this by housing our Celsius variable within the brackets of the float command. And when we run this script, you should see the value you typed in was originally a string, but has now been converted into a float. If we uncomment the Fahrenheit line and run the script again, we should no longer see any type errors. The second way to do this isn't really any different to what we've just done. It's just neater and more concise. Instead of typecasting the Celsius variable, we can typecast the input directly. This can look a bit confusing at first, but what we're doing is simply nesting our input command within our float command, and Python reads lines like this from the innermost bracket outwards. So first Python will run the input command and wait for the user to reply. The keyboard input is then directly sent to the float command, which converts it to a floating point number. This then finally gets stored into our Celsius variable. So we've basically achieved what we did before, but now in one step instead of two, and we can now delete the typecasting on line 6. The last step is to print the result of our calculation to the screen. If we run the code like this, we get another type error. This time the problem lies within the print command. Within the brackets, we're adding two items together. Since Python is a strongly typed language, we cannot add together two or more items that have different data types. So to solve this, we need to do some more typecasting. Now we need to cast Fahrenheit back into a string data type, and we do this with the string command to turn it into a string data type. And that's our complete script. Even though this script works and does what we ask of it, it cannot yet handle a user that doesn't want to play by the rules. So instead of a float or an integer, I decide to type in some text after the prompt. This program will break. This program isn't yet flexible enough to analyze our input. It simply assumes we'll provide a suitable value and nothing else. We can solve this by using conditional statements or if statements, and I will cover this a bit later on. But in essence, these if statements can check variables and decide what to do next based on their value. For example, if the user input is anything but a float or an integer, explain to the user that they've entered an incorrect value and ask them again for input, and keep looping through this if statement until the user behaves. When they finally do enter the correct value, then continue on with the rest of the script as normal. In this section, we're going to cover the most common arithmetic operators you'll find in Python programs, and I'm going to show you how to apply them to variables. Now, before we perform any mathematical operation on variables, you need to ensure that their values are stored as numerical data types, in other words, as floats or integers. In this section, we're going to assign values to variables manually, for example in the code. But if you're expecting input from an external source, like the keyboard or a file, you need to make sure to typecast these values into floats or integers. And this is something I showed you in the previous section. So let's start with two variables, which we'll call A and B, and give them some integer values. Now we have previously covered the addition operator, which simply adds two or more values together. And when we add A and B together and assign the sum to C, we get the value of 19. And this value is also an integer data type. We can change the variable A into a decimal number or a float, and our sum now changes to a float as well. So basically we can see here that you only need one float within a sum to turn the result into a float itself. And it doesn't matter how many integers you have in that sum. This also applies when we subtract variables. So if I subtract A from B now, we get a value of 9. But if A and B are both integers, the variable C will be an integer itself. But if I change A now into 14.0, C will also become a float. However, in terms of data types, division is different. If I set A to 10 now, and leave B as 5, and divide A by B using a /, we get a value of 2.0, which is a float. And this is counterintuitive because 10 divides evenly into 5, leaving us with exactly 2, which is a whole number. And of course, if we divide two numbers that don't divide evenly into one another, we get a decimal number. And as you would expect, this would be a float. We have another division operator that uses two /. This is called the floor division and returns the whole number part of the division. So, for example, 14 divided by 5 is 2.8, but if we use the floor division operator, this will return the value 2 before the decimal point and will totally ignore the numbers after, and the result is an integer data type. Multiplying two integers together will result in an int data type, and we use the asterisk for the multiplication. And again, if one variable is a float, the multiplication will produce a float too. If you want to raise a variable or a number to a power, we use two asterisks. And finally, the modulus operator returns the remainder of a division. So we know that 5 divides into 14 two times, with 4 left over. And 5 also divides into 12 two times, with a remainder of 2. In the last section of this video, we cover the mathematical operators most often used in Python. But what I didn't cover was what Python does when you have more than one operator in the same expression. For example, how does Python sum this expression? Does it multiply the 3 times 4 first, or does it minus 3 from 14 first? There is in fact a definite order that Python calculates these expressions, and it's called operator precedence or order of operations. And you may have heard this term before when you studied maths in school, because it's also used in algebra. So in the expression above, Python multiplies 3 and 4 first, then minuses the result from 14. The multiplication operator has a higher priority than the minus sign. But let's imagine we want the 14 minus 3 to be summed first. We can place brackets around them. Everything within brackets is evaluated first, because the brackets have a greater precedence than the multiplication symbol. So let's list the order of precedence of these operators. We have brackets, exponentiation, the multiplication, division, floor division, and modulus all have equal priority to each other. Addition and subtraction also have equal priority to one another. Let's try a few more examples. So here I've included an exponential to our expression above. Looking back at our list, brackets is first. So even though we have a subtraction in the brackets, everything within the brackets is summed first, and we ignore everything outside the brackets for now. The exponential is next. Then we multiply. If we rearrange this expression and place the times 4 into the brackets, we read off the sum as follows. First, we focus on the sum within the bracket. So multiply 3 by 4 first. Then minus the sum from 14. Then finally square the result. Now there is one thing about the order of operations that really confused me at first. And that was why multiplication and division, as well as addition and subtraction, have equal priority. In other words, what do we do when we have a sum like this, where multiplication and division or addition and subtraction are back to back? If operators have equal priority, what order do we sum these numbers? When we're dealing with a situation like this, we have to sum the values from left to right. For example, in this new expression, we start from the leftmost operator first. So 4 minus 8 is minus 4. Then we add 5 and get plus 1. The same is true for the next expression. We divide 2 by 5 first, then multiply the result by 5 to get a value of 2. Python also has a number of built-in maths functions that come in useful. The ABS function returns the absolute value of a number. This means that whatever number you have between the brackets, positive or negative, this function will always return a positive. So for example, the variable a is a positive 12. When we execute the absolute function, it returns the value unchanged. But if I change b to minus 18.1, we now get a positive number. We can also round decimal numbers to the nearest integer. So here I've changed the values of a and b. And first we'll round the value of 12.5. So in this example, any value between 12.0 and 12.5 will be rounded down to 12. But anything above 12.5, like our example 12.51, will be rounded up to 13. We can also round to a specific number of digits by adding the number of decimal places we want to round to within the round function. For example, if we want to round 10.443 to 2 decimal places, add a 2 within the brackets after the comma, and our answer gets rounded down to 10.44. And if we want our final number to be rounded to 1 decimal place, we get 10.4. Another thing we can do is find the largest item in a list or group of variables using the max function. Max will return the value of the largest item. On the other hand, the min function will return the smallest value. If we want our program to perform more complex maths, we need to import the math module. Now I'll talk about modules in a lot more depth later, but essentially a module is a file that contains Python code relating to a specific topic. So for example, the math module is a separate Python file that contains many different mathematical functions that we can choose to use in our program. Modules are very useful because they can be reused for many different programs written by many different people. The maths functions in the math module do not need to be written from scratch every single time you want to use them. You just need to import the module. And again, I'll cover this topic a bit later because it's very important to learn how to use modules and how to create your own. So to import the math module, we need to use the import statement. This is saying, locate the math module and import everything from that module into this project. There are other ways to import modules which I'll explain later, but this is the easiest way to understand at the moment. If we look online at the Python documentation, they provide us a list of all the functions available in this module, and I put a link below. Because there's so many here, I'm only going to show you a few. So first, let's find the square root of a number. To do this, we use the square root command. and when we execute this, we should get the answer of 5. We can also truncate numbers with the trunc command. This command will return a value within the brackets, with the fractional part removed. In other words, it will round down the number towards 0. So for example, truncating 25.9 will give us the value of 25, and truncating minus 2.9 will give us minus 2. Do at least have a read through the other maths commands within the Python's documentation. As you become more familiar with Python, you'll find that a lot of functions have already been written for the type of problem you want to solve, so it's worth hunting around online for a bit before writing a command yourself. That being said, there are many more Python modules that you can import into your projects. In fact, when you install Python, you also installed a library of these modules, and you can view them here on the Python module index page. And if you can't find what you're looking for here, you may be able to find what you need from the Python package index, which is a huge library containing everything from code on artificial intelligence to web development. I even found code relating to stock analysis. So we've covered strings very briefly in the variables and data types section, and we use the addition operator to add two variables together that contain strings. But there is a specific name for this process, and it's called string concatenation. Take the following sentence. Here we're using the addition operators to piece together a sentence using three variables which are stored in the program. However, when dealing with longer sentences, concatenation can be unwieldy and errors can creep into your code. For example, this code will give us an error because we're trying to add together string data types and an integer data type. Strongly typed languages like Python do not allow us to do this. Now we can just cast the email variable to a string data type, which we've done in previous sections using the string function. But there is a cleaner way to do this. We can use the string format command, where our code now becomes this. So this performs a formatting operation on our string. The curly brackets act as placeholders for the variables first name, last name, and email. But since the introduction of Python 3.6, there is in fact a more readable and computationally efficient way to do this. And that's by using formatted string literals, which are better known as f-strings. So f-strings are prefixed with an f just before the opening quotation mark, and the variables are now placed between the curly brackets. I've also previously talked about having the choice to either use single quotes or double quotes when printing out a string or saving a string to a variable. Now there is a good reason for this. Say if you decide upon single quotes and have this sentence. The apostrophe here prematurely terminates this sentence. Everything after the word Tom is not understood by Python. We can use an escape character or backslash before the apostrophe to tell Python we don't want it to be treated as part of the code, but this can become difficult to read. So an alternative is to use double quotes to start and stop sections of text. And single quotes can now be used as apostrophes. And of course, if you want to indicate direct speech using double quotes, you can open and close the text with single quotes. If we want to store larger sections of text that span across multiple lines, we can use 3 single quotes or 3 double quotes. Now, with our poem, or any other string for that matter, we can check if a certain phrase or character is present in the string. So for example, in our poem, if we want to see if the word heart is within this poem, we can use the keyword in, and this will return a Boolean true or false value. And we can use this Boolean value later in conditional statements if we want to make decisions on what to do next. For example, if we had a whole bunch of Edgar Allan Poe poems, we could search through them all and see how many times references were made to the word heart. In Python, strings can be indexed. In other words, when you create a string, Python automatically assigns a numerical value to each character's position in the string. So for example, each character in this string has an index value. The first character T sits at index 0, the second character H at index 1, and so on. And we can use these indices to extract certain sections of the desired string. Let's do a few examples. If I wanted to extract the fourth character, we would place a 3 between the square brackets after the variable name. And we use a 3 instead of a 4 because indexing always starts at position 0. So if we now place a 0 in the square brackets, we should get the character T. Indices can also be negative, and these start counting backwards from the end of the string. So the last character has an index of -1. So when we print out my string at index -1, we should get the letter G. We can in fact slice multiple characters at once to create a substring by inserting a colon into our square brackets. Let's say we want to extract the first 4 characters from my string. What we're saying here is we want to start at index 0 and extract all the characters up until, but not including, index 4. You might also see it written like this, where the 0 has been excluded. We can also slice the last 6 characters from this string by starting at the 17th index and leaving it blank after the colon. And this blank or empty space simply means continue on until you reach the end of the string. One thing worth noting about strings is that they are immutable. In other words, a string cannot be altered by trying to assign a character to an index position. So if we wanted to change the capital T at the start of the sentence to a lowercase t, a completely new string has to be created. So taking this example, we would do this. Here we're taking all the characters from my string except the first, and then concatenating the lowercase t to the front. This is then assigned to our new string variable. Length is one of Python's built-in functions that counts the number of items in a sequence. Examples of sequences can be lists, dictionaries, tuples, and so on. And I'll cover these a bit later. But we can also use the length command to count the number of characters in a string. So general zip codes should be 5 characters in length. And if we add our zip code variable as a parameter to the length command, we should get a value of 5. But we can also combine the length function with one of Python's inbuilt string methods. And the string method we're going to use will check if all the characters in our zip code string are digits. And this will return either a true or false value. So if I add a random character now, we should get a false value. There are about 50 string methods that do a variety of different things to strings, but I'll only cover 3 more in this section. So the next method returns a title-cased version of our original string. This will capitalize the first character of every new word. The count method allows us to count the number of times a specific substring occurs within the larger string. So if we take our previous poem, we can count the number of times heart was mentioned. And finally, the replace method replaces a specified phrase with another phrase. So if we use our poem again, we can replace heart with soul. So far in this video, we've looked at programs that execute lines of code one by one from top to bottom. Once the final line has finished executing, the program stops. But programs like this are rather inflexible. They cannot vary their actions to new and unexpected input. To write useful programs, we need the ability to check conditions. In other words, to check if something is true or false. So if our program finds a condition to be true, then execute a specific block of code. But if this condition is false, then execute a different block of code. This ability to be able to choose what blocks of code to run allows our program to change its behavior. Let's start off with a simple example. Say we want to create a simple script that will turn on some lights if it's nighttime. This is the most basic type of if statement. Here we have an if keyword, which must be in lowercase, and is directly followed by a Boolean condition. Now, whatever comes after the if keyword, it has to evaluate to either true or false. At the moment, we've just placed a Boolean variable here, but later, I'll show you how to add more complicated Boolean expressions. Immediately after this condition, we have a colon, which indicates we've finished writing the condition. After we hit enter, most Python IDEs will automatically indent your cursor by 4 spaces or a tab. Now this indentation is really important in Python. It's a way of telling the Python interpreter, which is the program that executes our source code, that a group of statements belong to a particular block of code. So our print statement saying it's time to turn on the lights belongs to our if statement. But the print statement that says this will display no matter what is outside the if statement block, and this is because it's not been indented to the same position. So let's run this code. Here, both messages are printed into our shell. Our nighttime variable is set to true. Our if statement evaluated the condition, saw it returned a value of true, and therefore gave the Python interpreter the permission to run the indented code block beneath. This print statement isn't tied to our if statement and therefore executes regardless of whether the if statement finds the condition true or false. If I want another piece of code to run in our if statement, I have to make sure it is indented by the same amount as all the other code in this block. So what happens if we set nighttime to false? We now see that the text, it's time to turn on the lights, and now I can see, doesn't get printed. What if we have a situation where we want our code to execute something else if our condition returns false? We can use something called an else clause, which is an optional addition to our if statement, and again any code written beneath must be indented. Because our nighttime Boolean variable is false, when we reach the if statement, this block of code isn't executed, but the second block under the else statement is. Changing the variable back to true, this first part is now executed, but the indented block under the else clause is ignored. We're not limited to just using Boolean variables for the if condition. We can in fact compare all kinds of values or expressions after the if keyword. Say if we want to control a car's speed using a cruise control system, we'd have 2 values that we'd be interested in: the car's current speed and our desired speed. If the speed is too low, we'll want to accelerate. If too fast, we'd want to decelerate, and so on. But we'll need the ability to compare 2 values, and we can do this using relational operators. For example, are they exactly equal to one another? Not equal to one another? Is one less than or greater than the other? Or maybe less than or equal or greater than or equal to the other? When we place these relational operators between 2 variables, the expression will return a true or false value. For example, 25 is not exactly 30, so we get a false value. But when we want to see if 25 is not equal to 30, we get a value of true. These relational operators become useful when used on variables whose values can change. So let's incorporate this into our if statement. So here we've set our car's speed to be 25 miles per hour, and our desired speed is 30. When our program reaches our if statement, it evaluates this Boolean expression. It's asking whether our current car's speed is less than our desired speed. In this case, this returns true. So the print statement start accelerating is executed. Everything in the else clause is ignored. Let's change the car's speed to 90 miles an hour now. Our Boolean expression now evaluates to false, and the else clause is executed. There is a bit of a problem here. There is no way of knowing if we've just reached 30 miles an hour or far exceeding the speed limit. The if-else code block only gives us 2 options, but in this situation we really need 3. One to accelerate if we're less than the desired speed, another to decelerate if we're above, but a final one to do nothing if we're exactly at 30 miles an hour. It sounds a bit counterintuitive at first, but we need to tell the car to stop what it was previously doing if it has reached its goal. We can add this third condition using an elif clause, and we can have as many elif clauses as we want after the if statement. So first, our car is travelling at 25 miles an hour, which is lower than the desired speed. This means that the first condition returns a true value, and the print statement start accelerating is executed. The condition after the elif clause returns false because our current speed is not greater than the desired speed. And the else clause will run only if all other conditions above are false. Basically, the else clause works as a catch-all. If we change the speed to 35 miles an hour, our first condition returns false, but our elif condition returns true. And finally, at 30 miles an hour, both the if and elif conditions are false, so our else clause will run. We can make our if statements even more versatile by including the logical operators and, or, and not. In this example, we use both the logical and operator as well as a couple of relational operators to decide if Tom can buy some alcohol. In the first condition, we test if Tom's desire for a drink is true, and whether he is above or equal to the legal drinking age. When using the AND operator, both of these sub-expressions have to be true for the following print statement to execute. If either one or both of these sub-expressions are false, we skip and move on to the elif clause. If Tom wants a drink and he's below legal age, we print out this F string. But if Tom doesn't want to drink, we can skip again to our final else clause, where age doesn't matter. The logical OR operator behaves differently. Now, only one of the sub-expressions have to be true for the whole condition to be true. So for example, when you leave for work in the morning, you may consider whether you should take your umbrella with you. So this condition here will evaluate to true in 3 separate scenarios. If it's raining now and it won't rain later, if it's not raining now but it will rain later, and if it's raining now and it will rain later. This condition only returns false if it's not raining now and it won't rain later. And lastly, the NOT operator allows you to invert the truth value of a Boolean expression. So here, we have 2 Boolean variables, one indicating whether we own a car, and another saying whether we've failed our driving test. Because the NOT operator inverts the value in our failed driving test variable, the if condition reads, if failing our driving test is not true, and we own a car, we can go driving. In all other cases, there will be no driving today. It can take a while to get your head around the if statements, so it's important to practice them as much as possible. The best way to do this is to start writing your own simple scripts and get used to searching for help online when you get stuck. Now, so far, we've only covered ways to store single values within variables. For example, if we wanted to keep track of all the shopping we wanted to buy, we could assign each food item to appropriately named variables, but this is not very efficient. What we can do instead is group them together into one of Python's built-in data structures called a list, and then assign this list to a single variable. So, for our shopping list, we would enclose all our items between square brackets, separated by commas, and assign it to a variable called shopping list. If we print out our list, we see our list displayed exactly how we typed it in the code above. So our list here contains items that all have a string data type, but we can use a mix of data types at the same time. Let's expand our shopping list to include the price of each item. Lists have a lot of similarities to strings. For example, lists can be indexed and sliced. If we want to print out the first item in our shopping list, we'd use index 0 in square brackets after our variable name. And to get its price or the second item on the list, we'd use index 1, and so on. And just like strings, to access the last item in the list, we use a -1. Slicing lists uses the same process we use with strings. We can slice this list by using a colon. So extract beer and its price into a new list. We would type this. And remember, our item beer starts at index 2, and we want to include everything in our shopping list up until but not including index 4. But we do have to be careful when trying to index an item that doesn't exist. We've only got 6 items in this list, and the index ranges from 0 to 5. If I try to extract an item at index 6, I'll get an error. To avoid this somewhat, we can see how large our list is using the length command, which we used previously in the strings section. But unlike strings, lists are mutable. This means it's possible to update values directly without needing to create a new list in the process. Say, for example, we want a more expensive loaf of bread. We can directly update our shopping list by referencing the index. So here, we've directly overwritten the last item in the list. And again, just like with strings, we can concatenate lists. For example, if I create a shopping list and you create your own shopping list, we can combine them together by using the addition operator. And what if we have a really long list and we want to see if we've added candles for our cake? We can test if an item exists in our list or not using the keyword in, and we can use a simple if statement to add the candles if they're not present in our complete list. So let's break down what we've done here. When we print out our complete list for the first time, you can see we've forgotten the candles. Within the if condition, the in keyword is given the element candles and is told to search for that element in the sequence. If it finds a direct match, it will return true, otherwise it will return false. If the candles are absent from the list, we run these 2 lines of code. What we're doing on the second line is adding a new list with our candles and price directly to the complete list. And we're using something called a shorthand operator. This is equivalent to writing this, but it's quicker writing it out using the shorthand operator. So in other words, we are taking our original complete list, concatenating a new list, and then reassigning all of this back to the same variable name. Python also has quite a few list methods that come in useful, and you can see them all here, and I've got a link below, but I'll show you a few so you can see how to implement them. The append method adds a new item to the end of the list. This is equivalent to the list concatenation before, where we added candles to our complete list, but the difference here is the append method simply modifies our existing list. The concatenation method creates a completely new list that has to be reassigned. In other words, the append method is less cumbersome and quicker to execute. We can count the number of times a specific item appears in a list, so we start with the name of our list, followed by the dot operator and the count method. Whatever item we want to count in our list is placed between the brackets. Sort is another useful method. If we want to sort our pets list, the items will be reordered in alphabetical order. In a list of numbers, they are sorted from lowest to highest. We can sort in reverse order by adding reversed equals true as a parameter in our sort method. Tuples are very similar to lists, but there are a few key differences. Like lists, tuples consist of a number of values separated by commas, but tuples are always enclosed in parentheses rather than square brackets. Another key difference is tuples, like strings, are immutable. In other words, once we've coded the tuple, we cannot modify its values when the code is running. We do not have any insert or remove methods like we do for lists, and we cannot assign a new value by referencing an index value. This is actually quite useful if we're working on a larger project with multiple programmers and we want a sequence of items to remain fixed. Indexing does work exactly the same as it does with lists. So if we want to access an item at the beginning of the tuple, we'd reference index 0, and at the end of the tuple, we would call index -1. Slicing works exactly the same way as well, where here we're slicing out values at indices 1 and 2. We can also concatenate tuples as well, and the result generates a new tuple. There are only two inbuilt methods we can use on tuples. The index method will find the index position of the first instance of the item it can find. So in this code, I'm searching for the index position of the value 72, which happens to be at position 3 in the tuple. However, if the item we're searching for doesn't exist in our tuple, we'll get a value error, and this will prematurely halt the execution of our code. So it's always a good idea to run the index method between try except statements, which will catch any errors without breaking our code. We'll cover try except statements shortly, but here's just a quick example of what you can do. The count method works exactly the same way as it does for lists. It counts the number of times an item is found in your tuple. So here, we have only one 81 value in our ages tuple. But if I add 3 more, our count method now returns the value of 4. You can think of dictionaries in Python as kind of a lookup table. Let's say we want to store airport names with their corresponding airport codes. Here, we have a dictionary called airports that contains 4 items known as key value pairs, and we've surrounded them with curly braces. Each item consists of a key and a corresponding value, and these keys and values must be separated by a colon. If we want to create a new key value pair, we need to add a comma and either start on a new line or you can add it on the same line. With the airports dictionary, each item has been placed on its own line, simply to make the dictionary easier to read. One of the main differences between dictionaries and other data structures like lists or tuples is that values within a dictionary are referenced using a key instead of an index value. If you remember back to the lists section, in order to access an element in a list, like this one, we'd need to know its index position. But with a dictionary, we can access stored values by referencing a key. So for example, if we wanted to know where the airport CTA is located, we'd type in the key between square brackets, and it returns us the value part of the key value pair. Now, in our airports example, both our key and our value are string data types, but we can pretty much use any data type with a couple of exceptions. The values can be anything you want, whether that's a boolean, integer, float, or even more complex data types such as lists or dictionaries. The keys can be any immutable data type. In other words, they can be strings, integers, booleans, floats, and even tuples. This can get complicated rather quickly, so for the remainder of this section, our dictionaries will only comprise of keys of int or string data types. Duplicate keys are not allowed in dictionaries. If we add FRA 3 times to our airports dictionary, Python will ignore the first and second instance of the key and only acknowledge the last in the dictionary. Now you have to be careful here because Python will not throw an error if you accidentally add 2 or more identical keys in your dictionary. It will just print off the last occurrence. So if we now try to reference a key that doesn't exist, we get a key error, and this will stop the execution of our program. To get around this, we can use the get method, which returns a none value if the key isn't found. But most importantly, our program won't terminate unexpectedly. We can change or update a specific value by referring to its key name. So if we wanted to change the value Fran back to Frankfurt, we can directly assign this value back to the dictionary. We can even add new items to a dictionary in this way. So if we wanted to add London Gatwick, we could create a new key within the square brackets and assign a value directly to it, and it will add the key value pair to the end of the dictionary. That's going to be it for now on dictionaries, but I'll cover more later when we get to the loop section. A while loop in Python is a control flow statement that allows code to be executed repeatedly based on a given Boolean condition. So the basic syntax for a while loop can be written like this. The code in the while loop will be executed as long as this condition is true. Once the condition becomes false, the while loop will stop executing and the program will continue with the code after the while loop. The structure of while loops have many similarities to if statements. For example, a colon is used to indicate we've finished writing our condition, and all indented code beneath belongs to the while statement. And again, it's really important to remember the code to be executed must be indented by the same amount to let the Python interpreter know that those statements belong to the while loop. You might use a while loop to print out all the elements in a list as long as the list is not empty. In this code, the condition for the while loop is myList, which will be considered true as long as the list is not empty. The code in the while loop pops an element and prints it. This will continue until the list is empty, at which point the while loop will stop. Now I've included a list method called pop that we didn't cover in the list section. The pop method will remove the last item from the list every time it's called, and my list will shrink in size. Let's try another example. This while loop prints out the numbers 0 to 9. Here the condition for the while loop is I less than 10. Because we've set I equal to 0, the condition in the while statement evaluates to true, and the code blocks in our while statement are executed. Inside our while loop, we print the value of I, and then increment it by 1. Our I variable now stores the value of 1, but we can't break out of the while loop yet because our condition still evaluates to true. So our while block gets executed again, and this repeats until I becomes equal to 10. The value 10 isn't printed because the condition returns false. Now it's worth noting here that if the condition for the while loop is always true, the loop will continue executing indefinitely. This is generally not a good idea, as they can cause your program to crash or hang. We can use something called a break statement to exit the loop prematurely, even while the condition is true. This can be useful if you want to stop the loop based on some condition. So for example, this code here represents a simple guessing game. It will keep asking the user to guess a number until the number they've chosen is exactly equal to this number to guess variable. In which case, the condition in this if statement returns true and then runs the break command. This will exit you out of the loop and run the print command saying you've won. There is another statement you can use in while loops called the continue statement. This is used to immediately skip the rest of the current iteration of the loop and move on to the next iteration. This is best understood with an example. Let's say we want to print out all the odd numbers between 1 and 10. First, we set up our while loop with our condition. This condition is currently true because our counter is less than 10. Once in the while loop, we increment our counter by 1, and then we use an if statement to check if our counter is evenly divisible by 2. In this condition, we use the modulo operator, which we covered in the maths section. Here, the condition returns true if our counter value divides exactly into 2, with no remainders left behind. When this occurs, the continue statement skips over everything else in the while statement and starts again at the top. This means that we only run the print counter command when the counter is odd. In other words, when it doesn't divide evenly by 2. The second type of loop in Python is the for loop. For loops iterate over a block of code a predetermined number of times. This can be useful because you don't have to test a loop condition every iteration like we had to with our while loops. And this often makes for loops easier to write. Take this example. Here, our for loop iterates over each element in the number list, one by one, until it reaches the end of the list. On each iteration, the number variable will be assigned the value of the current element in the number list, and the block of code within the loop will be executed. In this case, this block of code simply prints the value of the number variable to the screen. And this number variable can be named anything you like. For example, I could rename this to items. We just have to make sure we name it to something that makes sense. And remember, lists can hold multiple different data types at once. So if we quickly modify this list to hold some strings, booleans and floats, these too will be printed out. We can also iterate over another type of sequence, such as a string. So here, we are doing exactly the same thing as before, but we're iterating over each character in my string and printing them out one by one to the shell. So if we want to iterate over a specific list of numbers, but we don't want to have to type them out manually, like in our first example, we can in fact use a new function called range. The range function is a built-in function that is used to generate a sequence of numbers, and it takes 3 arguments: a starting value, an ending value, and a step size. The starting value is the first number in the sequence. The ending value is the last number in the sequence, and it doesn't include the ending value itself. And the step size is the amount by which the numbers in the sequence increase. So if we start at 1, end at 10, and step forward by 2 each time, we get a sequence of odd numbers from 1 to 9. We can use the range function in our for loop to print us out all the odd numbers from 1 to 10. And if you remember back to the while loop section, we got the same result with this while loop. As you can see, the for loop does this in far less code and is easier to read. The third argument in the range function is optional. If we remove it now, our Our for loop will print out all the numbers from 1 to 9. We can also iterate over a sequence of items in a dictionary. So this dictionary has 3 keys: name, age, and city. And each key has a corresponding value. Our for loop cycles over each item in our dictionary and uses the values method to pull out the value part of each item and stores it in the value variable. The print statement then displays the result to the shell. If instead we want to print out all the keys, we could replace the values method with the keys method. Now for loops can be much more complex than this, but I'll leave that for a more intermediate course, and I won't cover them here. And next we're going to move on to functions. A function is a self-contained block of code that performs a specific task. They're effectively like mini programs because they contain everything they need to perform a well-defined task. We've actually already seen some built-in functions in this video. For example, we've used the print function to display messages in the shell. The input function was used a few times to get keyboard input from the user. We've used the length command to count the length of strings and lists. All these built-in functions were written by developers of Python, so we didn't need to code these elements ourselves from scratch. When we call one of these functions in our script, Python executed that function's code, and that code is held in one of the source files somewhere in your computer. We've also used methods, which have helped us out in a similar way. For example, we looked at how we can determine whether a string variable contains only digits, and we did this by typing out the variable name, followed by a period, and then the method name. However, the difference with a method is it's always called on an object, whereas a function is standalone and can be called by itself. You don't have to understand this now because we'll be covering methods in far more detail a bit later. Sometimes the built-in functions will not be enough for your project. You'll most likely need to create your own custom functions, and that's what we're going to do now. First, to create a function, we need to use the def keyword, followed by the name of our function. All the functions must end with parentheses, which we'll make use of in a bit. And a colon is used to signify that the indented code beneath belongs to the function definition. And just like with the if statements and loops, the block of code that belongs to a particular function definition must be indented by the same amount. So I've called this function my function, and it contains 2 print statements. If we run this code as it currently stands, nothing will happen. This is not because we've made a mistake or there's an error, but simply because this is just a function definition. We haven't yet told our program that we want to run this code, or even in what situation we want to run this code. Let's give the end user the choice as to whether to run this function or not. We'll need to get input from the keyboard, and we'll do this with the input command. We're asking the user if they want to run the function. Whatever the user types, which could be anything, gets stored in the answer variable. Now we need to use an if statement to make a choice. If the user typed a y, this condition returns true, and we call my function beneath. When the function is called, everything within the function is executed. The elif and else statements handle all other inputs the user could have entered. But this example shows us one of the first reasons why functions are really useful. We can call my function in many instances throughout our script, but we only have to write the function code once. This becomes more useful when our functions become more complex. And it's important to note that the function definition must always be written above the function call, because the Python interpreter reads the program from top to bottom. If it arrives at the function call first, before encountering the function definition, it won't know what the function is, and it will throw a name error. we can make our function more versatile with the use of parameters. Parameters allow us to send values directly to a function. Say we want a program that gives us the ability to calculate the area of a circle by asking for a radius. We'll start by using the input function to collect the radius from the user. Here, we're typecasting the input string to a float variable. We do this because all the return values from the input command are strings. Next, we want to create a function that can perform our calculation and print the result to the shell. Within the parentheses, we've added a parameter called radius, and it's simply a variable that will eventually hold our chosen radius value. We pull in the radius parameter and then calculate the area. Here, we're squaring the radius parameter and then multiplying it by the constant pi, which we've defined above. We then print this to the screen. Now I've decided to use something called a format specifier. This forces Python to print out the chosen area variable to 2 decimal places. If you want to print out to 1 decimal place, you would change the value here to 1. Currently, this code won't do much until we call our function. We need to call our function under our input command because we need to ask the user for an input radius first. We've typed the name of our function, and within the parentheses, we've added something called an argument. This is the value that we want to send to our function, in our case, our chosen radius variable. We can in fact add multiple arguments and parameters to the function. Take this example. This is very similar to the previous example, but now we're adding 2 parameters. We can make functions even more versatile now by asking them to return the result of a calculation. This now allows us to treat functions as complete black boxes. In other words, you can use these functions without needing to know how their internal code works. Let's try a slightly more complex but more useful example of a function. We want our program to ask for an integer and then tell us if it's a prime number. So first, we use our input command as before. Next, we write our function definition. Our function has one parameter called number, which will store our integer value. This number is then passed into our function. First, if the number is less than 2, we know it's not a prime number, and we return a Boolean false value and exit out of the function. For all numbers between 2 and our chosen number, we check if any numbers divide evenly into our number. If they do, we know we don't have a prime number and return a false value. In all other instances, we must have a prime number, and therefore we return a true value. This does look confusing, but one of the great things about functions is that they're self-contained. If you're using someone else's function, you don't really necessarily need to know how they work. You just need to know how to call them. Because our function definition returns a value, either true or false, when we call our function, we often assign it to a variable. Here, our function collects our user input as an argument and spits out a value, which we can store in a new variable. And because this function gives us a true or false value, we can also use it in if statements as a condition. As you start creating more and more user-defined functions, you'll run into the problem of variable scope. Variable scope refers to the visibility and accessibility of variables within a program. As your code becomes more complex, you'll have some variables that can only be accessed within the same block of code they were defined in. For example, a variable defined within a function only exists in that function. It cannot be called or used from code outside that function. This type of variable is called a local variable. Let's jump into a simple example. We've created a simple function that defines a local variable called local variable and prints out its value to the shell. We then call our function below. Here, we've successfully printed out the message and variable to the screen. But if I try to access this variable outside the function, I get a name error. Local variables, even though a bit confusing, are very useful because they keep our function self-contained. Everything you need, like variables, calculations, and logic, are locked safely away within the function. The function has complete control over its code. Global variables, on the other hand, are visible and accessible throughout the entire program. And this is because they're defined within the main body of the Python code. In other words, outside any function. I can print this global variable outside of the function, and I can print it within the function. The variable is global. It can be accessed throughout the entire program. In general, we want to try and avoid these global variables as much as possible because it's hard to keep track of all the variables and their values at any given point during runtime. When we restrict ourselves to local variables, our code is easier to keep organized and modular. A module is simply a file containing a collection of functions and variables that you can use in your Python programs. And these modules are really useful because they allow us to split our code into smaller and more manageable chunks, which can make it easier to write and maintain. Let's jump straight into an example. First, we're going to look at creating our own custom modules. Then we're going to explore modules that already exist and that can be downloaded from the web. I've opened up a folder and I'm creating 2 Python files here. Our first Python file will contain our main program. This will be the program that we'll use to launch our project. The second Python file is our module. This module will contain standalone functions that we can use in many different projects. Notice here that both files must end with the file extension .py, and these files are in the same folder as one another. I'm going to put in 2 functions into our module. The first function takes in a string as an argument and tells us whether the first character of our string is a vowel. If it is a vowel, it returns a Boolean true, and if it's not, it returns a false value. Vowels is a list that only exists in our function. We cannot call this outside our function. Just after our return keyword, we're taking the first character from our string at index 0, converting it into lowercase with the lower method, and then seeing if it exists in our list. Our second function checks if a string is a palindrome. In other words, a word or phrase that reads the same backwards as forwards. And we use this instruction within square brackets to reverse the order of the string. If the original string and the reverse string are exactly the same, we have a palindrome. Now, you don't necessarily need to know how these functions work right now. The more you practice using Python, the more these will make sense. But the point here is to learn how to use modules in your project and why they're useful. You might agree that both these functions could be useful in many different projects going forward and that they're highly reusable. So, how do we call these functions into our main project and make use of them? We can import a module into our program using the import keyword. When we created our module file, we named it myModule. So to import this file into our project, we simply type import my_module. And again, this file must reside within the same folder as this main script file. We can call the functions defined in the module using the dot notation. And here, we've typed in the name of our module, followed by the name of the function we want to use. We've also added a string as an argument to our function. Now, this line of code here is effectively just copying and pasting everything within our module file to the top of this code file, but the import keyword allows us to do this in a much cleaner way, and it makes our scripts easier to read, especially if our module file grows to be thousands of lines long. We can also test out the other function as well. So here, I'm testing out if this title starts with a vowel. And as you can see, it returns true. But we're not limited to just functions. We can add in other data structures like variables, lists, dictionaries, and so on into our module. So opening up our module again, we could add this dictionary. We can now access elements of this dictionary in our main script by using the dot operator. If we have an extremely large module, we might not want to load everything into our project. We might only want 2 or 3 functions out of the possible hundreds within the module. And when we import a module, Python loads the entire module into memory, which can make our program run slower. To get around this, we can import only the specific functions or data structures that we need. And we can do this using a slightly different notation. For example, if I want to import just the employee dictionary and the is a palindrome function, we would use the from and import keywords together, and we would separate each element by a comma. So effectively, we're saying, from my module, only import is palindrome and employee, but nothing else. But now, when we want to call these functions, we leave out the dot notation. In other words, we just call the functions by their names, as if those functions were written in our main script. In some instances, you may see modules imported like this. From module name, import star. The star tells the Python interpreter that you want to import everything from that module. And this is exactly the same as saying import module name. The only difference is that the import module name forces us to use the dot method to access functions. For example, here we have to state what module the employee dictionary comes from using the dot operator. On the other hand, if we use from module import star, we can write out the function names like this, where we can exclude the name of the module and the dot operator. Whatever method you choose is up to you, but by using the dot notation, it's easier to see where the function originates from. Now we're going to discuss some of Python's built-in modules, and if you want to see a complete list of them, you can look over this site here. One of these modules is the random module, and it provides many functions for generating random numbers, but I'm just going to cover 2 of them here. You can explore the rest of them from Python's documentation page. The easiest way to import this module is to just type import random. Let's say we have a list of numbers and we want to select one number at random. We can use the choice function from the random module. And notice that we're using the dot notation here. You can see that every time we run this script, the choice function will choose a number from the list in a seemingly random order. Now this choice is not truly random, but it's good enough for games, simulations, and statistical modeling. You would never use this random module for cryptographic purposes or generating random passwords. There is another module for that purpose. Another useful function is the shuffle function. With this function, we can reorder our list into a random pattern. Now, Python has a large number of built-in modules, but they might not contain what you're looking for. In this case, there are many online modules that you can install using pip, which is the package manager for Python. For example, if you want to build a website, or you want to explore data science, or do web scraping, or anything else for that matter, you'll most likely find a module for your project online. You can search for them here. To get these packages, you must do a pip install, and I'm going to show you how to do this now. If you installed the Thonny IDE at the start of this video, it's really easy to install these packages into your project, but we can also use the command line as well. So let's say we want to create a 2D platformer game. we would need to install a module called Pygame. If we try to import it into our script, like so, we get a module not found error. So we can go to the Python package index website and search for Pygame, and they will provide us with a command that we can copy and paste into our command prompt. After hitting enter, the pip package manager will install all the necessary items to make Pygame work on our system. Alternatively, we can install Pygame through the Thonny interface. If we click on Tools and then Manage Packages, a search field will pop up that will allow us to search for a package. After clicking on Search, our Pygame module is the second option in the list. Click on that and then click Install. After the installation is complete, we should no longer get an error message when we import Pygame. So I've just copied and pasted this simple Pygame script from this website, just to show you an example of how to get up and running with this module. If you want to follow their tutorial to the end, they show you how to get a simple game up and running. But they do cover concepts like object-oriented programming, which I'll cover a bit later in the video. An exception is an error that occurs during runtime. Examples of exceptions could be when our program tries to divide by 0, or when it tries to access a list element that doesn't exist. If anything like this occurs, our program will crash and ultimately upset the end user. So our goal as programmers is to try and catch these exceptions as they happen and handle them gracefully. Try except statements allow us to do this, and they're especially useful when working with external resources, such as reading from a file or making a network request. And it's because these operations can often fail due to factors outside our control. So let's try a simple example. In this code, we are dividing two numbers together, and at the moment, 10 divided by 5 will give us a sensible response. But if y changes its value throughout the program, we could land ourselves with a division error. For example, if we change y to equal 0, we are now trying to divide by 0, which is not allowed in maths. And when we run this code, we get a 0 division error. To get around this problem, we can nest this code within a try except block, like so. So here, we place all the code we want to check in the try block. And the except block contains our backup code if our try block raises an error. And notice here that after the except keyword, we've named the type of error we want to catch, which in our case is a 0 division error. Running this code again, with y equal to 0, we get the message cannot divide by 0 in the shell. But this division line can also generate another type of error. Say if x or y was changed to a string data type at some point during runtime, we cannot divide an int and a string together in Python. And when we run this script, we get a type error. So to catch this error, we can type in type error as one of the exception classes we want to catch. We've also updated our print statement because now our exception block handles both types of errors at the same time. If you want to handle these exceptions individually, you can place two exception blocks one after the other, like this. And this is probably the better method, because we can more easily see what went wrong with our program. You can start to see now that part of your role as a programmer is trying to anticipate all these possible errors, and the larger your program gets, the harder this becomes. If you don't know what other types of errors you may encounter, you can just put a plain except keyword, and this will catch all other possible errors that could occur. But this is generally bad practice because it can hide important information about the exception, and it makes it difficult to understand what went wrong. Instead, it's usually better to define specific exception classes in your except blocks, like we demonstrated in the first examples. In this last example, We have a dictionary of colours, where the keys represent the name of the colour and the values are the corresponding hex values. Within our try block, we're trying to search for the key named orange, but since this doesn't exist in our dictionary, we get a key error. We catch this key error in our except block and use this opportunity to add this new colour to our dictionary. In the following section, we'll examine techniques for handling data from files, and we'll continue our use of try except statements. So far, all our data has been held in variables and data structures within our program. Once our program terminates, that data is lost. It's often useful to store things like results of calculations and to do this permanently in an external file. And in this section, we're going to cover how to do this with text files. First, we're going to read from a text file that sits within the same folder as our main program. In this folder, I have my script, which I've called main.py, and a text file called my_text. I'm going to open up my Python script now and write some code that will read in the contents of my text file. To do this, we need to use the inbuilt open function, which accepts two arguments. The first argument is the name of the file we want to open. Now, because our file resides within the same folder as the script file, we do not need to type in the full address of the file location. But if our file was stored in another folder somewhere else, we would need to put in the full file address into this argument, for example. But notice what I've done here. I've placed a lowercase r before my string. This tells Python to treat the string as a raw string. If we don't do this, these backslashes will be treated as escape characters, and this will mess up our address. The second argument tells our open function what operations it's allowed to perform on our file. For example, R indicates we want to treat our file as read-only. If we try to write to it, Python will raise an exception. W opens the file for writing only. If the file doesn't exist, it will be created. If the file does exist, it will be overwritten. A also opens the file for writing only, but all write commands will append data to the end and not erase the original contents. And finally, the open function returns a file object, which we can store in a variable. And here I've called that variable text file. This object file variable now represents our file my_text, and we can use a number of different methods to manipulate the data inside. But opening files like this is now considered a less favourable method because it can lead to problems if an exception is raised while working with the file. It's generally considered a better practice to use the with statement to open and close a file. Now we can perform various operations on the file within the indented block. When the block is finished, the file is automatically closed. It also means we don't have to remember to call the close function when we're done. So let's see what's finally in our text file. To do this, we use the read method, which returns the entire contents of the file as a string. We can then store this string into a variable. Printing out our variable, you can see we have a shopping list. Now, I did say in the previous section we were going to use try except statements with our files. So let's do that now. What possible errors could arise while trying to read a file on a computer? Well, maybe someone moved, deleted, or renamed a file. Let's do this now and see how our program responds. So when we run this code, we get a file not found error. So let's add this exception after our except keyword. Now you probably noticed that when the file was not found, the print content statement also throws an error. What I've done here is include an else block within our try except statement. Everything within the else block runs if no exceptions occur. So when Python tries to open a file and succeeds, it will jump to the else clause. If it fails, it will run the block of code after the except keyword, and it will skip the else clause and continue if there's any code beneath. We can also have another problem with our text file. What if we don't have the permission to run it? Maybe this file is reserved for the administrator. In this case, we get a permission error, to which we can add the permission error exception class. I'll remove the try except statements for now, so that the following code is easier to read. But in practice, you would want to keep them in to make your code more robust. Let's say we want to read only one line at a time from our text file. We can use the readLine method. Here, we're calling the readLine method, which reads the first line of our text file and stores it in the contents variable, and then immediately prints it out. But when we call the readLine method again, it will read the second line of text. If we want to store each line into a list, we can use the readLines method, where here we've added an empty list, then use the readLines method to populate our list with every line in our text file. You've also probably noticed that our list also contains new line characters that are usually hidden within text files. These characters are generated when we hit the return key. We can strip these new line characters out by using a list comprehension. List comprehensions are more of an intermediate topic, so I won't cover them here in any detail. Let's now append items to our text file. So we're using the open command again, but the second parameter is now an A, which stands for append. When we call the write method on our text file, we'll append these two text strings to the end of our text file. But as you can see, blueberries and pears are not on separate lines. We have to add a new line character either before or after a string to ensure they're stored on their own lines. And one last thing before we finish this section. If we want to totally rewrite our text file, we would replace the second argument with a W. This will also create a second text file if we modify the name here in the first argument. So that brings us to the end of this short Python course for beginners. If you found this useful, I'd really appreciate if you hit the like button. And maybe think about subscribing if you want to see more Python videos on this channel. In fact, if you're interested in diving a bit deeper into Python, I have two videos here that will show you how to create graphical user interface applications. One is a random password generator, and the other tests whether your password has been pwned. If you have any questions, don't hesitate to reach out in the comments, and I'll try and help you out as soon as possible. And as always, thanks for watching, and I'll see you soon.